When it comes to electric power, it's important to first understand what the basic definition of power itself is before we make the connection between electricity and electric power. And in general, power is the rate at which energy is expended, and the expending energy is just work, so performing work. It's the rate at which work is performed. And to kind of visualize power, you just need to think about two situations: one where you walk up a flight of stairs, and one where you run as fast as you possibly can. You will probably notice that in one of these situations, when you get to the top, you're fairly relaxed, you're not out of breath. In the other one, you're probably out of breath, you're sweating. And that begs the question, what is the difference here? A lot of people tend to want to say that you expended more energy in this case, um, or that you perform more work. But when you think about it, you have a certain mass and you raise that mass, in this case, 5 steps. Well, in this second example, you also have the same mass and you raise that mass 5 steps. So the actual energy that you expended or the amount of work you did is exactly the same. Because at the end of the day, in either case, you raise your mass from the ground to the top of the stairs. Just like in this case, you did the same thing. So why are you so tired in the second case? In the first case, you seem to not really have expended too much energy. What comes down to our physical definition of energy versus the definition of energy that we like to use in our daily life. Like, I'm zapped, I have no energy left. That doesn't directly relate to the actual amount of energy we expended. The difference in this case is that while the work was the same, the time in which that work was performed is different. So in this case, despite the fact that the work or the energy expended in both cases is the same, in this case I had a significantly longer amount of time that I expended that energy, and in the second case I expended that energy in a much shorter amount of time. And that's the difference here. It's that concept of power. I exerted or expended more power in this case, which is why I was able to do the same amount of work faster. I did the same thing but faster, I therefore had more power. Just like if you had two cars and you race them down the track, well, they're both going, let's say, 100 meters. The one that can do that faster must have the more powerful engine. The rate at which work is done is power. So the general equation for power, as we said, is the rate at which work is performed, so work divided by time. You could also write it as the change in energy over time. And the unit of power is watts. So when you take a look at like a 60-watt bulb, that's basically telling you how much energy you're going to get per second or per a certain amount of time. When it comes to electric power, it's the same concept, except it's how much electrical energy is being utilized in a given amount of time. Because we have Ohm's law, which is V equals IR, we can equate power. It's the same basic equation, but we can relate it in terms of the electrical circuit variables that we know. So if you'd like to calculate the electrical power in watts of a certain device or a certain circuit, you are just going to have to multiply your current times your voltage. You could also square your current and multiply it by resistance. You could also square your voltage and divide it by the resistance. It's a fairly simple equation. You really just have to plug and chug. And I'll give you a quick example. So let's say you have a television at home. It has a total resistance of about 200 ohms. Whatever circuit is inside has a total resistance of 200 ohms. And you plug it into a 120 volt wall outlet. Basic type of questions would be how much current passes through that television as you utilize it, and what power does the television consume. So in the first case, that's a more basic problem. We just have to use Ohm's law. We know the voltage and the resistance, so I can therefore solve for the current, which is the unknown, and I find that about 0.6 amps of current will pass through this television as it's operated. How much power does it consume? Well, at this point, we know that we have the voltage, the resistance, and the current. I can therefore use any one of these three equations, and you'll see in any one of these cases, I'm going to wind up with the same answer. So this television uses 72 watts of power. That's the basic calculation for how much power something uses. What's more important to our daily life is how do I use that number to actually calculate the cost of electric power? So your parents pay the electric bill each month. How is that number actually generated? I'm going to show you a quick example because it's not that difficult. We'll take a look at two houses. They each have the same television. It's about a 300-watt television. In one household, they use it for 2 hours a day. In the other household, they watch it for 6 hours a day. And the main key here is that since time is a component, there's a difference in the amount of use in each house. Obviously, that has to be incorporated into our calculations. And power companies use what's known as a kilowatt hour. So you basically take the power rating of your device, multiply it by how long you've used it, and that's how you get this kilowatt hour. I'm going to show you how this number is calculated for these two houses, as well as how we figure out the final cost. So the first step is always going to be to convert your power output to kilowatts. For both House 1 and House 2, I was given 300 watt televisions, so we're just going to divide that by 1,000 to convert to kilowatts. It's just easier, and this is the term, the variable, the unit that power companies use, so always make sure you convert to kilowatts first. Once you have your kilowatts, to get kilowatt hours, you just multiply by how long you've used that device. So in House 1, which uses it for 2 hours, I multiply my power output times the 2 hours I use it, and I get my total kilowatt hours for this household. I'll do the same for the second house using the 6 hours, and I get about 1.8 kilowatt hours. That's what the power company is going to charge. It's going to charge the power rating of the device, the power output of the device, times how long you've used it. Each power company is going to have its own price. Generally, it's like cents, like 12 cents to 18 cents, somewhere in there. So let's assume the power company in this area charges 12 cents per kilowatt hour that you use. Well, House 1 had 0.6 kilowatt hours. When I multiply that by 12 cents, that means that every day they will spend 7 cents on the electricity to power their television. The second house, same rate, however, they have much more power used, so they wind up spending about 21 cents per day to use that television. It doesn't seem like a lot, but when you think about every appliance, every device, every computer, every cell phone charger, when you start to use all these things in your house over the course of a month, over the course of a year, you can start to see why a power bill might be maybe $100 a month, $200 a month. Things like that. Obviously, probably more expensive during the holiday season when you have more lights out, decorations, things like that use electricity. So when you add up all those small things, it does tend to be more than these small values you see here. So just to quickly rehash, if you want to calculate the cost of power, convert the power rating, which is usually in watts on a device, to kilowatts, multiply it by how many hours you're using that device. You'll have to do a little research or be given how much the power company charges, and then you can therefore find your total amount in dollars that you will have to spend to buy the electricity from a power company.